This is another convergence test that was not on the AP test this year, but normally is. It's called the integral test, and it will fit in very easily with what you already know about improper integrals. This will set up the theory for why the test makes sense. Consider this series, the harmonic series. Of course, you could write each term as being multiplied by 1, which I've written in blue. So 1 times 1 plus 1/2 times 1, and so forth. But if you look at it this way, if you write it this way, you don't have to do this. It just makes it clearer for a beginner. If you look at it this way, you can think of each of the terms in black ink as a height, and each of the terms in blue ink, or each of the numbers in blue ink, which is always 1, as a width. And if you think of it that way, then every single term is the area of a box. Height of 1 times the width of 1. Height of 1/2 times the width of 1. Height of 1/3 times the width of 1. And you've seen this kind of pattern before, ever since the beginning of integration, when you first learned integration way back in Calculus AB. It's the idea of summing up the area of a bunch of rectangles. The first rectangle has a height of 1, the second has a height of 1/2, and so forth. So this is that familiar Riemann sum idea, where this is like the height, or y, and then what's in blue, the 1, is the width, or delta x. So you've seen this idea before. And in fact, this is a Riemann sum approximation of what function. Well, look at this. 1 over 2, 1 over 3, 1 over 4. How would you write this series? It's 1 over n. But if you were thinking in early calculus language from last year, you would think of it as y equals 1 over x. That's what's in green here, is the curve y equals 1 over x. And this is a way, this would be a right or a left-hand box approximation of the area under the curve y equals 1 over x. Right, so this is a Riemann sum. This original series can be thought of as the Riemann sum for this set of rectangular boxes. So here's a way to write that in math notation. The sum of the series 1 over n, this series 1 over n, can be written with every term times 1, and that's an approximation of this integral. And notice, this is a type of integral you would not do in AB, because it has an infinity symbol here. This is an improper integral, and this is one of the reasons we learned about improper integrals earlier in the year, so that you could understand the integral test. Now let's look at this particular one. You already know from your work with improper integrals what this integral does. Does it converge or diverge? And if you have to think about it, pause the video. Well, this particular improper integral diverges, and you can see the way I've drawn this. This is a diverger, and this series, this area of all these boxes, would have an area bigger than the area under the curve, starting at x equals 1. So if the area under the green curve diverges, and the area of the black rectangular boxes is bigger than that for any subsection, for any selection of it, then it's obvious that the area of these boxes has to also diverge. You could never buy enough paint to paint all these boxes. And that brings us to the idea of the integral test. Now there's more to it than this, a little bit more to the theoretical setup, to the requirements, but I don't think it's very important. I never teach it in any year. This will always work for every single AP problem I've ever seen. Let's say you're given a series. That's the general way of saying each term of a series, a sub n. But if you can write these terms, if you can write that, what goes there is a function of n, a continuous function of n that you could integrate. So we'll write continuous, not something, say, stepwise or discontinuous. If you could write this as a continuous function of n, which you can like 95% of the time or more, if you can write it like that, and that's what I mean by a continuous function of n, a sub n equals f of n, then, and here's the payoff, here's what you have to know to do this test. The series and its corresponding improper integral both do the same thing. Okay, series from 1 to infinity, improper integral, 1 to infinity. Now, I want to put here in a circle, some people write it like this, and you will see books that write it like this. You might get a professor that writes it like this. Instead of using x as the variable, they'll use n as the variable. So you have f of n dn. Nothing wrong with that. That's equivalent. The College Board tends to do it this way, so does your book, so I tend to do it that way, but either is fine. So what this test says is that both of them do the same thing. What do I mean by same thing? What it means is they both converge or they both diverge. It's impossible for one of them to converge and the other to diverge. So what you would do is write the equivalent integral and look at it. And based on your skills with improper integrals, you can determine if this converges or diverges, and that immediately tells you what this does. So they both converge or they both diverge. That's what I mean by both do the same thing. Now, your brain might naturally jump to a conclusion here, which is that, hey, I can evaluate an improper integral, so then I could find the sum, right? And the answer is no. The sum of the series is not the same number that you get with the improper integral. They don't work out to be the same, and you kind of saw that. The boxes always have a width of 1, so it's not a good Riemann approximation. It's not going to converge to the same numerical value. However, they will both either converge or diverge. They just won't converge to the same value. So this is a big warning. Don't let your brain fall into this trap to think that the sum of this series is equal to the number you get by evaluating the improper integral. Okay, here are 3 examples. You may want to pause the video and just look at the top row of this and see if it makes sense to you, see if you could do it using the integral test. All right, and I will proceed. What you do is, to make the integral easier for your brain to understand, we replace the letter n with an x. So then I get these 3 integrals. Now these should look extremely familiar because they're always the 3 integrals I put up as examples to understand for doing a quick improper integration, for doing a quick evaluation of it. You've learned rules for this. So see what happens. You get that, rewrite it as an integral. There you find the antiderivative and look at its extremes. Do the same thing here and here. And then you come up with these 3 familiar answers. In this one, we've got x, so it's popped up into the numerator, and it's getting bigger and bigger and bigger. Therefore, what does this do? It diverges. Therefore, the original series also diverges. Look at this one. What does this do? Well, that's why it's so important to know the graph of natural log. Y equals ln of x off the top of your head. That increases without bound. There's no horizontal asymptote. So this diverges. Therefore, this diverges. And then finally, if that exponent down here is bigger than 1, positive exponent bigger than 1, then the x, the function of x, stays in the denominator. So as x gets bigger and bigger and bigger, this makes it go to 0. So you have 1 over 1 and 1 and 0. So this converges. It actually converges to the number 1. Converges, which means this converges. Now this does not converge. The sum of this is not 1, as I said before in the big warning. All right, you might be sitting there saying, wait a second. These are all p. I didn't need the integral test to do this. I've already learned the p-series and the p-series test. Here, p is a half. That's less than 1, so it diverges. Here, p equals 1, so it diverges. Here, p is greater than 1, so it converges. I don't need all this. Well, what you do have to know in case you take more calculus is the reason we know that, the reason we know the rule for the p-series is from the integral test. When you learned that a few weeks ago, the rule for the p-series, I just told it to you. I didn't prove it at all. I may have hearkened back to our improper integrals, but we did not use the integral test to prove it. But that's how you prove it. You write a function as 1 over x to the p, do the integral, and we talked about this earlier in the year, and you can show that if, and p stands for positive, right? So this will never be like negative. P won't be negative 2. That would be silly. So you can show that if p is less than or equal to 1, this improper integral will diverge, and therefore so will the series. If p is greater than 1, this improper integral will converge, and therefore so will the series converge. And then finally, we'll do one last example where it's not a p-series. So take a look at this. You can try this. You should try this on your own. Pause the video, and now I'm going to do it. So to make it easier to look at, we'll rewrite it using the letter x. And I'll bring this up and rewrite it with a negative exponent to make it easier to think about because we're integrating involving an exponential. Your first guess at doing this integral might be integration by parts because you see 2 parts, but go back and think of an easier method. That is the derivative of this exponent, give or take constants that we don't have to worry about. So that immediately suggests u substitution will be the easiest way to do this. So we'll say u equals x squared. Then du equals, right down here, du equals 2x dx. Right? And we can look at this. When x is 1 here, u will be 1. As x gets bigger and bigger and bigger, so does u. So we don't even have to change these numbers as the limits of integration. Now, to make this, I'll go quickly here. I want it to be 2x, so I'm going to put a 2 there, and so I put a 1/2 out front. And of course, that won't really have anything to do with whether it converges or not, but that's just for completeness. All right, so I get this integral, 1/2 times the integral. As I said, sometimes these will change, especially this one may change, but here it doesn't because it's just u equals x squared. Right, that's the du right there, 2x dx du, and this is e to the negative u. So e to the negative u du. Now we've changed it into an integral that's very easy to do. 1/2. All right, we'll do this integral. Right, so it'll be e to the negative u with a negative sign. So we'll put the negative out front, and it's e to the negative u. I'm going to write it this way so it's easier to think about. Right, and the question now is not to evaluate this, which we could, right? But not to evaluate it, but to ask the question, does this converge or diverge? Well, the one is no problem, and as u gets bigger and bigger and bigger, this approaches 0, so the whole thing converges. Therefore, the original function here converges.